Let us obtain a Fourier cosine series for the function fx equal to x in the interval 0, pi. That means x is changing from 0 to pi. And then we need to show that 1 by 1 square plus 1 by 3 square plus 1 by 5 square plus dot 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 equal to pi square by 8. Let's do it. First of all, Fourier cosine series is given by Fourier cosine series is given by fx equal to a0 by 2 plus summation of n goes from 1 to infinity an into cos nx. Of course, this is in the interval 0, pi. Now, if we can compute a0 and an, then we are done. We need to determine the coefficient a0 and an in order to determine the Fourier series. So, first of all, we need to determine the Fourier cosine series. Here, fx equal to the function which is simply x. And we have formula for the coefficient an, that is given by 2 by pi integral 0 to pi fx into cos nx dx. Fx into cos nx dx. So in this case, fx equal to 2 by pi, fx equal to x, and cos nx as it is. So, an is given by, in this case, an is given by 2 by pi integral 0 to pi fx is x into cos nx dx. Now, this is a product of two functions, so we have to apply integration by part. So, let's recall integral of u into v dx is given by first function which is u as it is, and then integral of v dx, and then minus integral of derivative of first function u dash into integral of v dx, and the whole product has to be integrated again. Therefore, integral of x into cos nx first function is x, integral of cos nx, integral of v is sin nx by n, minus integral of derivative of first function, derivative of x is 1. Integral of v, integral of second function, integral of cos nx is sin nx by n dx. That's equal to x into sin nx by n minus 1 by n, that's constant. Integral of sin nx is minus of cos nx by n, of course with some constant of integration. Now, if we want an, it is 2 by pi integral 0 to pi, so we have to put the upper limit and lower limit. Therefore, an equal to 2 by pi integral from 0 to pi x into sin nx by n, sin nx by n, minus minus plus, so plus cos nx by n square. 2 by pi, that's just a constant. When I write x equal to pi, sine n pi is 0. So that's just a 0. Cos n pi is minus 1 to the power n by n square as it is. So we have computed the integral for x equal to pi. What about for x equal to 0? When I take x equal to 0, 0 into sine 0 is 0. When I take x equal to 0, cos 0 is 1 by n square as it is. Once again, we can take 2 by pi common, and you are left out with minus 1 to the power n minus 1 by n square. When I take n equal to 2, minus 1 whole thing square is 0. Minus 1 whole thing square is 1. 1 minus 1 is 0. When I take n equal to 4, then also this quantity is 0. When I take n equal to 6, then also this quantity is 0. When I take n equal to 8, this quantity is 0. So this is simply 0 for n equal to 2, 4, 6, 8, and so on. For every even n, this quantity is 0. What about odd n? For odd n, 2 by pi is 2 by pi only, n square is n square only, and minus 1 to the power n, minus 1 to the power 1 is minus 1, and minus 1 will give you minus 2. Minus 1 to the power 3 is again minus 1 and minus 1 will give you minus 2. And minus 1 to the power 5 is again minus 1 and minus 1 will again give you minus 2. So for odd n, this is just minus 4 by pi n square, n equal to 1, 3, 5, 7, and so on. So we have computed an, but what about a0? Let's do it now. a0, now the formula remains the same. a0 is given by 2 by pi 0 to pi fx into cos nx dx, but n is 0, cos 0 is 1. So a0 is 2 by pi 0 to pi fx dx. a0 equal to 2 by pi integral 0 to pi fx dx, and that is equal to 2 by pi integral 0 to pi fx is just x, so x dx, and that's equal to 2 by pi integral of x is x square by 2, and the limits are 0 and pi, so this is 2 by pi into pi square by 2. And when we cancel pi and 2 out, we are just getting a0 equal to pi. So we have computed a0 and an. So why don't we write Fourier cosine series now? Therefore, Fourier cosine series of fx equal to x in the interval 0, pi is given by Fourier cosine series for fx equal to x in the interval 0, pi is given by fx equal to, so let's write the formula once again, a0 by 2 plus summation of n goes from 1 to infinity an into cos nx. Of course, in the interval 0, pi. In this case, fx equal to x, a0 is just pi, so pi by 2 plus n goes from 1 to infinity. As we have seen earlier, if we take n odd, then an is 0. So we will, if we take n even, then an is 0. So n goes from 1 to infinity, but in this sum, if I take n even, these are all 0, so we'll just take n odd. N odd. N goes from 1 to infinity. When n is odd, an is given by minus 4 by pi into n square and cos nx. So an is known, then cos nx. Well done. We have obtained Fourier cosine series in the interval 0, pi only. So this series is valid only for x lying between 0 and pi. Now, second part of the question says, and then show that 1 by 1 square plus 1 by 3 square plus 1 by 5 square plus dot 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 equal to pi square by 8. Well, 1 by 1 square, n odd, 1 by 3 square, 1 by 5 square, these quantities are there. But apart from that, we have cos nx. When can we have cos nx equal to 1? We can have cos nx equal to 1 if x equal to 0. So take x equal to 0. If x equal to 0, 0 equal to cos nx is 1, rest of the expression remains as it is. Pi by 2 plus n goes from 1 to infinity, n odd, n odd minus 4 by pi into n square into 1. So that will give us minus pi by 2 equal to, let's expand this, minus 4 by pi, that we can write outside the summation, n odd. So we'll take n equal to 1, 1 by 1 square. N equal to 2 we cannot take, n has to be odd. So n equal to 3, 1 by 3 square. Take n equal to 5, 1 by 5 square. Take n equal to 7, 1 by 7 square, and so on. We can cancel minus out. We can take pi to this side, pi square by 8. So pi square by 8, pi square by 8 equal to, minus got cancelled, 1 by 1 square plus 1 by 3 square plus 1 by 5 square plus 1 by 7 square plus dot dot dot. And so we got this infinite sum to be just equal to pi square by 8.